So thank you very much for that magnificent introduction, and of course it's a great pleasure to be invited to speak to the General Council. So again, thank you very much for this invitation, especially in what is probably the best university building, really. So I intend to speak for hopefully about half an hour, just to give you some idea of the timing. And if you do have to check your iPhones for the rugby in between, then do it discreetly rather than tell me you're doing it. So I'm going to speak on the subject of managing and storing carbon. And as was mentioned, I am initially a geologist. And for a large part of my professional life, I've been responsible for getting carbon out of the ground, whether that be coal, gas or oil. And in the past 10 or 12 years, 15 years maybe, what I've been trying to do is put some carbon back into the ground for climate change reasons, which we'll look at shortly. And having attended the General Council meeting earlier on today, one of the pleasurable things about university is you can always learn something new. And I learned that part of our mission is to undertake significant, sustainable and socially responsible research to make a contribution to Scotland and the world, which is terrific because that's what I've been trying to do throughout my entire career. So it's nice to discover eventually that I'm on the right track. So I intend to do this through the medium of slides. Hopefully it's not too technical. Hopefully the visuals will be understandable by everybody. And then there's usually a strap line along the bottom of each one to make the main point. And what I'm intending to do is lay out what the problem is. Why are we interested in the problem? When should we do something about the problem? And how are we going to do something about it? And make the link between universities identifying a problem and also trying to provide solutions to the problem, because that's part of the role of the university in my lexicon, that we shouldn't just identify more and more problems and undertake more and more research, but also try and find a practical way forward. So as a geologist, I'm interested in geological time, and this is a graphic of geological time from the start of the Earth, which geologists believed was about 4,500 million years ago. And throughout most of Earth history, we have very little record. There are lots of hard rocks and soft rocks in the geological record. But the bit which humans are most interested in is from about 600 million years ago when life starts arriving, and we have the fossil record. And all the fossils that people know and love come forward to the present day. And where we are at the present day is a really very unusual period, and that's now being given the name of Anthropocene, which is technical name we don't need to bother with, but it's trying to signify that in this period of unique geological time is the first time when people have had a greater influence on the world than nature does. So the activities of humanity are tangibly affecting the way the world works, the way the ocean, atmosphere and climate interact with each other. And so we're living in a period of time where there's unprecedented change, unprecedented challenge, and part of the learning to how to tackle that challenge can, I think, be gained from looking back to the record in the past of geology to give us clues how to behave into the future, but also needs to be inextricably intertwined with engineering, with social science of acceptability to people, and unfortunately or fortunately economics and even politics. So, as many of you hopefully will agree, it's getting hotter in the world in general. This is a graph of world climate, world temperature from 1800 through to the present day. And you can see that the graph is slightly sparse with large error bars in the 1800s. But the trend is quite clear that if we take a 0 year at around 1960, 1970, then the world's been getting hotter and that temperature increase is accelerating. And the interesting thing about this graph is that this is based on 4 sets of independent information by 4 different groups worldwide, including one set of information by a group at Berkeley University in California who originated being a lot of physical scientists, physicists, and said, we don't believe what you environmental scientists and earth scientists are saying. You can't analyze data. This is rubbish. Give us the data and we'll do it properly. So the data was passed across, they analyzed the data, did it properly, and then said, you're absolutely right, the world is warming very, very fast. We're total converts to climate warming, and we believe it's happening, something should be done immediately. So this is a robust conclusion, is what I'm pointing out. And the conclusion from this is that if we superimpose this onto a graph of climate change, our temperature prediction by the Intergovernment Panel on Climate Change, this is historic historic carbon emissions, through time from 1850 to about 2000, carbon dioxide emissions per year, and business as usual from the Intergovernment Panel on Climate Change tracks along this red line, and future scenarios of sustainability trying to decrease carbon emissions for a sustainable future track along those coloured lines. But the unfortunate recent truth is that during the past 11 years, the actual world is tracking with known emissions, measurable emissions, at that red arrow. So it's tracking well above the worst case of the Intergovernment Panel on Climate Change. So this means that both the rate of climate change is accelerating because of carbon emission, and the total impact will be much worse than currently predicted by the Intergovernment Panel on Climate Change. Now, there's a common perception that we in the UK are immune from things because things only change slowly in the UK and we're surrounded by ocean, so this doesn't really matter to us. But that's not true. This is a graphic by the UK Meteorological Office, and this is effectively the long-range climate forecast for 2100. Okay, this is not the weather forecast for tomorrow, this is a prediction for 2100. And by 2100, the Meteorological Office states that the world, on average, will be, on average, 4 degrees warmer centigrade than we are now. And you can see the average warming is about +5 over Berlin, +3 over the UK, +7 over southern Sahara. But those averages disguise the peaks and troughs. Now, we could easily manage another 4 degrees centigrade here, quite equable, really, but the peaks and troughs are the problem. And if you read the report, what this says is that the peaks in the UK are that heat waves which are currently 38 degrees and newsworthy centigrade, as a heat wave in London, for example, by 2100, that heat wave will be peaking at 46 centigrade or more. Okay, so that is an African type of temperature, or to look at it another way, a couple of months ago in Tasmania and southern Australia, there were bushfires rampaging through southern Australia with a temperature of 40 degrees centigrade. So this is a very tangible signal that we can anticipate very large future changes in the world we're expecting to live in. The UK is not immune from climate change. The UK will experience highs and lows of erratic weather. So we do have a very severe interest in this, not to mention food security around the world, not to mention the movement of populations and shortage of water resources. We also have a stake in this in the University of Edinburgh, because we're all familiar with stories of claims of Enlightenment figures in Scotland, whether it be James Hutton inventing the science of geology to a large extent, or whether it be James Watt commercializing the steam engine. But we also have Joseph Black, who was a student at the University of Edinburgh, and Joseph Black, portrait in chemistry department here, was the person who first isolated what he called fixed air, first isolated carbon dioxide as a substance and gave it the name of fixed air. It was later given the more formal name of carbon dioxide. So he was a student here in Edinburgh, went across to Glasgow for a while, and then came back to be Professor of Chemistry in Edinburgh. So we have the responsibility, if you like, for discovering carbon dioxide, so we also have perhaps a responsibility for doing something about it. And there is a little bit of more recent synergy in that I think last year, when the grass was not there in the, 2 years ago, sorry, when the grass was not there yet in Old College, there was an excavation and some chemical glassware and materials were discovered, and I'm told very reliably that at that time the chemistry department may have been over here in what's now law, and these are probably some of Joseph Black's original materials. So we do have a nice closing of that circle. Okay, so we have some claims to inventing some of this. We have some claims then to inventing a lot of the Industrial Revolution. So if I'm the world's first professor of carbon capture and storage, then we're trying to actually do something tangible about this, because Scotland also invented the commercial oil industry with Paraffin Young by excavating the oil shales in West Lothian, refining that oil and forming integrated production to supply companies in West Lothian. These shale bings are the relics of that initial commercial industry. And of course, in Scotland and in Europe and elsewhere, in Ayrshire, like here, we're still busy excavating coal and burning it as fast as we can. And of course, the North Sea has saved us economically since the middle 1970s and was one of the top 15 oil provinces of the world. So we've produced a huge amount of carbon in the recent past. And since the Industrial Revolution, each of us has inherited the liability for more carbon production than anybody else in the world, in Scotland. So what does that mean in terms of the future? So this graph, it tries to show you the amount of tonnage of carbon geologists estimate in the world, that the world holds in terms of oil or gas or coal or other sorts of fossil carbon. And the purple bits are the bits that we've burned already. So the purple bits are the bits we've burned. You may hear about the prospect of oil running out, and I'm entirely not bothered by the prospect of oil running out because we're probably only a third of the way through. And even if oil does run out, then we've got 200 or 300 years worth of coal in not just the UK, but also in the United States and Russia. And we've busy recently now discovering even more hydrocarbon resources with shale gas and unconventional gas in the United States, in Poland, in Russia, and probably in China, so that we have more than enough carbon to fry the world several times over. Okay, so we're already seeing about 0.7 or 1 degree of warming committed to that by burning this small amount of fossil carbon. And if we carry on behaving in the same way and burn all of the remainder of the fossil carbon, which unfettered capitalism will encourage us to do, then we have no prospect of living in the world as we like it. So the problem is quite clear. Here's the largest power station in the UK, Drax Power Station, burns coal, forms on its own, forms about 5 to 7% of UK carbon dioxide emissions. Here's a local facility at Grangemouth, one of the largest hydrocarbon refineries in Europe, and that has numerous sources of carbon all over it and emits about another 1 or 2 million tons a year. So we're emitting this to the atmosphere. We're having free waste disposal into the atmosphere from all this carbon dioxide and other greenhouse gases that we're burning. And that seems like a big resource, the atmosphere, because it goes away up to space. But if you imagine, I want you to imagine if we liquefy the atmosphere, liquefy the air to a liquid, then the thickness of the atmosphere is thinner than the height of this room. The atmosphere is about 10 meters thick if it's a liquid. And we're dumping all of this stuff free of charge into the atmosphere. And that is what's having the effect on the world climate, and that translates through into acidifying the ocean, and we're well on the way to killing a large part of the ocean as well. So the problem is there, and the solution in essence is straightforward. We need to bottle it. We need to find a way of burning this without any consequences. But of course, easy to draw a diagram, much harder to do it in practice. So what are we going to do about that? So the University of Edinburgh is a world-leading institution. The University of Edinburgh has some very forthright scientists among its ranks, and it's also a university. It can address lots and lots of different aspects. It's not just going to do geology, it's not going to do just technology. We also have arts, social sciences, medicine. We have a whole panoply of skills in the University of Edinburgh. So we can address this in what I think are the usual three ways. We can undertake some research which underpins everything we do. We can also undertake some teaching of the next generation and of the present industrial generation. And we can undertake communication to business to try and influence what people are doing right now and people will do in the immediate future. And that circle of information translates round and round, and that's what knowledge exchange is really around nowadays, is trying to make sure that what we do doesn't stay in the university but gets circulated and outputted, and we also get feedback from business as to what they want to do and what they value. So we're doing this in several ways in the University of Edinburgh. I'm not responsible for all of these. This is a free market in the University of Edinburgh. To some extent, people invent things, and I'm very pleased that people are busy inventing things all the time. So here's a whole swathe of MSc courses in geosciences, which is my home school, and in engineering, and a lot of those are concerned with carbon. So we have a very active, proactive position on that. There are also carbon courses in the business school and in the law school, and we've several world firsts on this. We have the world firsts on MSc training, carbon management, carbon capture and storage, carbon finance, global environmental law. We've also continuing to move forward on that with online learning in global strategies, free online course for anybody to register worldwide. And in future, I'd like to seriously look at doing worldwide courses on energy and geoscience, the linkage between climate, environmental impact, and the way we behave with fossil fuels. Because making that information available in an authoritative way to a global commons, I think is a very powerful exercise of UK learning and UK expertise. So we also undertake this through business, and as many of you know, then we've setting up at Edinburgh, again not led by me, but the Edinburgh Centre for Carbon Innovation has the intention of linking business to government and researchers. It has the intention of building human capacity in low carbon skills to move forward and have the skilled people to do this work, whether it's accountants or whether it's building contractors, and also connecting companies with aspirations to the people and investment to enable them to do this. And right now, down in Drummond Street and High School Yards, a new building or renovated building is emerging. And on the architect design, it looks like that, and it probably will look something like that in about a year or so. And the university's accumulated some money, put some of its own money in and gained some private sponsorship to undertake that £10 million renovation and new construction to enable teaching, crossover meetings between these business, government, academic communities, and basically act as a communication, outreach and proactive prodding hub. And that's a collaboration, again, between University of Edinburgh, Heriot-Watt, Napier University, and funded both by Europe and Scotland. So we've got, although we may be a centre, we've got networks going out wider than just the University of Edinburgh. In terms of research, the bit I can claim some blame or responsibility for is the Scottish Carbon Capture and Storage Group, which, as was mentioned, is the largest single UK group looking at the geological and engineering aspects of how to reduce our carbon emissions. And you can see that, those of you who are closer can see that we're talking about the central North Sea, storing carbon dioxide underneath the North Sea, how to get the capture part moving faster with engineering, and looking at the ecosystem impacts of carbon dioxide capture and carbon dioxide storage. So again, this is a multidiscipline activity, and this again is a partnership at the moment initially between the University of Edinburgh, the British Geological Survey in Edinburgh, and Heriot-Watt University in Edinburgh. And the ambition is to grow that partnership across all of Scotland, to pick off the people who are interested and have the abilities and skills to engage to make this a global force in carbon capture and storage, because I believe we have all the right conditions here in terms of our resource, in terms of our intellectual and academic and business endeavour to do that. All we're lacking is the funding, which is still controlled by the Westminster government. So Edinburgh is undertaking a lot of research on this. This is my split. We analysed this last week, so this is not an official university split, but this is our estimation of the grant income for the College of Science and Engineering during the past 5 years. And all I'm trying to display here is that of that total science and engineering split, carbon-related activity, whether it's carbon capture and storage, carbon grants, carbon dioxide or energy grants, forms about 10 or 11% of that income during the past 5-year period. So it's a very significant and stable income. So a lot of people are working on this, not just me. So I asked the question at the beginning, why should we do something about this now? So we've got some research activity. Why is that particularly appropriate now? So I'll plot this a graph, a historical graph, and this is of carbon dioxide emitted per year in billions of tons around the globe. So 10 billion tons, 20 billion tons, 30 billion tons, and you can see that since the start of the Industrial Revolution in the 1750s, and then the commercial steam engine and the Victorian manufacturing and globalization of power and steam and electricity, that's an inexorable rise of carbon emissions. The International Energy Agency make a prediction of what's going to happen in the future, and they did that because of a British intervention by Tony Blair at the G8 Gleneagles meeting in Scotland in 2005, when Tony Blair had the foresight as Prime Minister to put climate change much more significantly onto the agenda of the international G8 community. So the International Energy Agency, which is funded by all developed nations and by some very, very large companies, make predictions of what's going to happen in the future. And here's a prediction of what will happen in the future on the same type of scale. So if we do nothing, we follow the red line. And that is not just for 2 degrees warming, not just for 4 degrees warming, but at least an average of 6 degrees warming. And I told you about 10 minutes ago what an average 4 degrees might mean in terms of spikes and troughs in terms of temperature. So 6 degrees of warming is not currently accurately predictable in terms of its effects. I share a school in here with lots and lots of climate modelers, and if we ask them to do that, they'll need another grant to do that. Okay? Now, there are pathways to the future. We obviously need to turn this over in terms of achieving sustainability, and the general perception from science-based evidence is that we need to get down to about 10% of these emissions by 2050. So out somewhere here by 2050, then we need to have got down to about 5 to 10 gigatons of carbon each year. Now, if we'd done that in 1990, that would have been a slow and gradational decline, because most of these emissions are referenced back to 1990 as a basis year, the year you start calculating from. We've not done anything significant since 1990. Lots of politicians and lots of negotiators have had lots of hot lunches and lots of aeroplane flights, but there's been very, very little or minimal progress. In fact, the rate of carbon emission has increased with the industrialization of India and China, and now the southern parts of the American continent, Brazil, Argentina, Venezuela. So rather than go down, our emissions have gone up. So there's no prospect of doing very much, achieving very much till maybe 2020. And you can see here what happens. We're still aiming for 2050, but the rate, the slope on that line is steeper. So the rate of decrease becomes more and more difficult. We have to decarbonize faster and faster. So the longer we delay, the worse it gets, in simple language. So that's a very tangible reason for acting sooner rather than later. But of course, as Al Gore laid out in his Inconvenient Truth film, to delay is very seductive. It's always better to just do tomorrow, just like you did today. But the more you delay, the more you have to pay later on. So the more we delay, the more difficult it gets. And that's why we in the UK are trying to do something now. And part of the university's mission is also to be part of Scotland. And the Scottish government has an ambition to, by the year 2020, this is the official Scottish government whisky, 42% proof 2020 whisky, because by the year 2020, we want to have achieved 42% reduction of carbon emissions from 1990. So that's the 42% 2020 combination. And you can, if you're an important enough bureaucrat or politician, you can still be given bottles of 2020 42% whisky to remind you of that Scottish ambition. And this, I think, is the most ambitious carbon reduction target in the entire world. This is more ambitious than the rest of the UK. And Scotland is on the way to doing this. It's doing this by decarbonising its electricity supply, which is the most sensible thing to do. And Scotland right now is producing about 35% of its electricity from renewable sources, which is an unprecedented revolution in just 10 or 15 years, and is a greater rate of change than anywhere else in the world, I think. So Scotland is on the way to doing that. Whether, again, it can continue to do that depends on if the rest of the UK carries on buying and providing the building capacity for that electricity. And the reason that we're decarbonising electricity first is that if we look at this pie chart of our emissions of carbon dioxide in Scotland, this green sector at the bottom left, about a third of our carbon dioxide emissions come from power stations generating electricity. That's burning gas and mainly burning coal in Scotland. And if we decarbonise electricity, then we can supply low-carbon electricity into houses, so you don't need a gas boiler emitting carbon from your local gas boiler in your house, because we can't capture that, but that's still a carbon emission. So we have to eventually to get rid of that. We can supply low-carbon electricity to industries and businesses for heating, so they don't need to burn carbon locally to supply their heating and power. And we also enable decarbonising of transport, because it's totally unsustainable to carry on driving around with cars, trains, buses and trucks emitting carbon dioxide out of the rear end of those. So those eventually will have to transfer to carbon-free power, which will probably be electrical power generated from low-carbon sources. So decarbonising electricity enables eventually the fixing and decarbonisation of all those other parts of the carbon dioxide emission spectrum. So this is the most sensible action. So that's what we're trying to do. And to encapsulate it in one simple graphic, what we're trying to do is look at mining of the fuel, whether that be coal at a coal mine, underground, or an open cast mine, or whether that be extraction of gas or oil from deep underground. That fuel is transported to a power plant and burned, and at the moment, as I spoke earlier, that fuel, that carbon dioxide is dumped into the atmosphere free of charge. Whereas what we're trying to do is build an equivalent size piece of equipment there to capture the carbon dioxide as pure carbon dioxide, 95% pure or better, so that minimal carbon dioxide becomes emitted, but we've had the benefit of the fuel, but without the emission. That carbon dioxide is liquefied by pressurizing and transported by pipeline 100 or even 500 kilometers to be injected deep underground in rocks filled with salty water. and those rocks are porous rocks with microscopic pore space in them, and those rocks are exactly the same type of rocks as Old College is built out of here in the University of Edinburgh. Porous sandstones. Each of these solid rocks of building this building contains about 20 to 30% of space inside the rock, and it's that space into which we'll try to inject carbon dioxide. And that, if we can get that to work, that's the biggest single action people can take in an industrialized society to reduce emissions very quickly. And that will reduce emissions by 90% at the power plant. And if we take the cycle, the whole life cycle from mining or extracting through to disposal, it will reduce by about 75% emissions along that whole chain. So even whichever way you look at it, this is a very, very powerful, direct and quick action working within the existing industrial and electricity distribution system. So if this is the single biggest thing we can do, apart of course from energy efficiency and insulating your houses, which I hope you're all doing, this is the biggest single action. What are we doing about it? Well, in the University of Edinburgh, in engineering school, we have people working on designing and running power stations. We have people who are building mobile equipment for testing the emissions of gases from power stations and testing carbon dioxide capture at power stations. And we're trying to devise new ways of capturing carbon and separating carbon, which will be much more efficient and much more effective than the present day ways. So in 10 or 15 years' time, we hope to put out this type of technology will be commercialized, and that will cut the penalties which are presently there, reduce those penalties by a factor of 2 or even by a factor of 5. So this will become very, very achievable. Carbon capture at power stations will be very achievable at very low cost. We're also looking at the storage part. Where do you put the carbon dioxide once you've captured it? And so here's a map of Caithness, Inverness, Aberdeenshire. Edinburgh's down here, obviously. And this is showing you the oil and gas fields offshore. These are the red dots. Okay, so there are many oil and gas fields, but what we've also looked at is the rocks in between those oil and gas fields. And for the first time, we've surveyed these, and these orange ellipses here are the locations of individual sandstones, the geographic locations underneath the seabed, 1 kilometre or 3 kilometres down under the seabed. That's the location of those sandstones into which each one we can inject liquid carbon dioxide. So it tells us about the amount of resource we've got, the space we've got underground to inject the carbon dioxide, and how much space we've got to do that. So for example, this one here, locally known as the Captain Sandstone, that will take 30 gas-fueled power plants injecting into that for 100 years. So that's the size of capacity we've got. So in simple terms, Scotland, we now know, has a very, very large capacity. This histogram shows you the amount of storage capacity of carbon dioxide versus country. So the UK, Norway, Germany, Spain, Baltic, France, etc. And present emissions from Scotland are really about 0.5 on this scale, or from the UK, sorry, about 0.3, 0.5, so that we can see that the UK in the blue and green, and especially Scotland in green, have a huge storage capacity for carbon dioxide. It is a European asset. It's a European scale quality of storage that we can offer, not just to people of Scotland or to the UK, but offer to all of Europe as a state, as a trading bloc. So in simple terms, the UK has 35% of carbon dioxide storage for all of the European 27 community. So this is a huge potential new industry building off the back of the offshore industry in oil and gas, using the same skills and expertise, but turning that to sustainable and carbon reduction purposes. And the last part of our activity, of course, is to communicate with the public, to communicate with government, to communicate with companies and business. And this is an example of one of those events held in Drummond Street, I think, or somewhere in the centre of Edinburgh. I can't remember exactly where this one was actually, but communicating with focus groups from the public in this case to find out what we're proposing, what do the public think about that, is that acceptable, if yes, that's good, if not, why not, to try and refine and understand what's needed. And publications come out of this to try and improve the public communication strategy, because it's extremely well known that in the UK and in all other industrial nations, engineers and scientists can invent really, really good, smart, efficient things, but the public eventually don't want them. So we have to solve the public wanting it problem at the same time as we're trying to do the designing and the expertise. In terms of what this means to Scotland, in terms of commercial projects, many people will have heard last year and the year before of the Longanet project in central Scotland around our largest coal-fueled power station. That very nearly got funded to do carbon capture and storage as one of the first projects in the world. That fell by the wayside, unfortunately, because again, the government could not provide enough money initially, though they're only a couple of £100 million short. But right now, in 2013, in February 2013, Scotland has 2 representatives out of the 4 into the present UK competition. So our present bids are for a potential industrial capture site at Peterhead Power Station, sending the carbon dioxide offshore to the Goldeneye field operated by Shell, using existing pipelines on an existing power station. So this is again a very well thought out, very well technically evaluated, relatively low cost proposition to get the UK on the road to doing this. And this would be the first gas-fueled power plant in the world to do carbon capture if that happens. And the second one is to build a new coal-fueled power plant at Grangemouth on a piece of vacant land at Grangemouth, and again to take that up through an existing pipeline which was evaluated for the Longanet project, which again Longanet's just very opposite to Grangemouth across the water, to use that existing pipeline, again use an existing pipeline offshore to a different storage site. And that's proposed by a United States company. So this, again, that's showing that the UK and Scotland is attracting global attention in doing this. And if either of these happen, these will be the first of their kind in Europe, because the very first in the world now is being built in Saskatchewan, Canada. So these will be 2 of the very, very early ones in the world if either of these happen. So this is not the only game in town. Looking at a slightly wider spread, the Americans, being Americans, would like to just carry on behaving as usual and might acknowledge that climate and ocean are changing, but their proposed remedy is to engineer their way out of it. So they would like to build all sorts of devices like artificial trees for capturing carbon out of the air. And of course this is technically feasible. You can do this, you can engineer anything you want, especially if you can send things into orbit, to the moon and Mars and back. So you can do artificial trees, but this will cost, instead of doing carbon capture and storage at power stations, like we're suggesting at maybe £70 a tonne to capture carbon dioxide, this would cost about £700 a tonne for carbon dioxide. So there's a substantial cost difference. That's not the end of the argument. We may need to do this, but if you can do artificial trees, why not use real trees? Okay, so we've set up a unit at University of Edinburgh, first in the UK, looking at biochar, which is taking the organic cycle of trees or crop growth, and instead of sending that rotting material once plant debris has been harvested or put in the ground, instead of just letting that become compost, we intervene and pyrolyze that, which is making smart charcoal, low temperature charcoal, and we can get some energy out of that, we can get some fuel out of that, and we can put a quarter of that carbon back into the soil. So that acts as a slow carbon pump. You're using the growing material, which you can grow in biochar, and undertake field experiments to show that that grows better with biochar-enriched soil. We can analyze the effects and specify the biochar laboratory in our laboratories up at King's Buildings in the University of Edinburgh, and we can manufacture biochar to specific types, so we know exactly what's happening, and we can do tests in real farms like this one in East Lothian, where we're turning crop waste into biochar to put back on the fields on this local farm. So this is a local activity, not a large-scale industrial activity. This is the sort of thing that villages, towns, developing economies can do. And lastly, to start finishing off, the ultimate backstop, if all else fails, something else we're starting to look at, is that we may have to resort to climate engineering, and this really is the last resort, to try and build swathes and swathes of artificial trees, to try and forest absolutely everywhere, to put iron and phosphorus in the ocean to change the carbon cycle of the ocean, or if you're NASA and the United States military, to put aluminium foil into orbit, or to make artificial volcanic eruptions by spraying aerosols of sulfur dioxide into orbit. But again, going back to the climate modelers and the people who understand the Earth system, asking the question, do you understand the consequences of this? The answer to that is quite clearly no. So this is a last resort, but it is of quite a dangerous type of space to go into, but unfortunately this will be spectacularly cheap. So there's nothing better than military enterprises would love to do than fly into the stratosphere with tens of airplanes each year doing sulfur missions. So I think as scientists we also have to put out some advice and information that there are some things you do not want to do as well as some things you do want to do. So to finish off, what I've said is we're looking at quite a bleak future. This may or may not be the fourth road bridge in 2050, but it's quite clear that we've got too much fossil carbon. We need to find pathways to change into the future. We need to reduce emissions. We need to look at negative emissions by putting carbon back into the soil or back into the ground. And we may have to engineer the planet. That does look seductively attractive. And part of the mission of the university is to teach the students, to help the businesses to do this, and also to carry on doing the research, which will take us through to the same place with a much brighter future in 2020. So that's what I've got to say, and I hope you understood at least some of that. Thanks very much. Questions, of course, yeah.
Well, thank you very much. That was really interesting. I'm sure there are lots of questions. This is a topic that many people feel quite strongly about. So we have time. So some questions. Yes, gentleman right at the back.
Is it on? Thank you very much for such a comprehensive survey. I feel overwhelmed by the magnitude of the problem, and I'm amazed and delighted with your optimism or the energy with which you approach this. One thing I'm a little bit puzzled about is described by some people as the elephant in the room, because we live in a society which is built on the notion of endless growth. And in a finite world, this really is not feasible. We talk about reducing emissions, but I wonder whether the problem might be simplified if we were to address not only the question of reducing emissions, but also reducing consumption. And I mean, one could theoretically take 50% of the energy consumption of this country out by rationalizing our use of energy. We could even turn the tariffs upside down so that low users of energy would command very low prices, and then the prices would accelerate. Instead, it's the other way around, so the energy companies are actually directly competing with you and encouraging people to use more energy. I wonder if you have any thoughts about tackling the underlying ills of society as a way of perhaps informing the process.
Okay, yeah. So again, that's in itself quite a big set of questions there. So I totally agree with your premise, basically, that I think the taxing or the pricing of energy is far too cheap. That's one reason people consume so much. We can have great gains in more effective consumption or being more efficient. And one of the obstacles to putting the price up is the fuel poverty problem, that you then force the lowest income 20% or the poorest house 20% of the population into not having enough heat and energy. And so I agree that I also think that reversing the energy tariffs would be a terrific idea. We could give out the first 1,000 kilowatts and then the middle classes might pay a bit more, and that would incentivize the middle classes to reduce consumption. On the underlying problem, I also agree that consumption is a critical problem, and we in the West and in Europe have constructed the argument to benefit ourselves so that we're allowed to consume anything we want without paying the penalty for it. So we can import material from China, or India or any other developing economy, whether it's plastic widgets, training shoes or clothes, and we don't have those carbon emissions in the UK because we only count what we emit here in the UK directly. So the UK government can religiously say almost every year that we have lowered our emissions, but that's not true, because we should be counting the embedded emissions in what we import, what it's cost to bring in those imports. And personally, I would like to see a performance standard on a lot of these, on many products. Like if you buy a washing machine, it's rated A to F on its consumption of electricity. I would like to see an A to F rating on the embedded carbon on what we're bringing in. And that would give consumers a lot of information to make some choices. And then thirdly, you talk about consumption as a way of life, and this is obviously goes back into prehistory almost, that we have invented ourselves as a consuming species. But we do have to find a way of consuming in a more circular, sustainable way, rather than digging things out of the ground, whether it be oil or coal or minerals or water. Then we have to find a way of making wealth by transferring goods and services to each other, or valuable things we value to each other. And then the final thing you didn't mention, which is incredibly controversial, of course, is that the final consumption is the number of people which are on the planet. So the planet can, in principle, support 6 billion or 9 billion people, but you have to consume more and more and more to do that. So the ultimate consumption, which is entirely politically unacceptable to talk about, is population editing. And I have no idea how you do that.
Not storage in the same way, clearly.
No.
Right, we have a question here.
Yes, I'd like to ask, you said that the carbon would be actually put into seawater. I don't know whether that gets altered in any way, but is there a danger from earthquakes that it could be actually exposed again in the future?
Okay, so I tried to not say we would put the carbon dioxide into seawater. I tried to say we would put the carbon dioxide through drill holes into rocks which were filled with salty water in these rocks, which are about 1 kilometre or 3 kilometres beneath the seabed. So putting carbon dioxide into seawater is again a last resort strategy, because that makes the seawater acid, and we will either kill the upper ocean, or we'll just have to wait for the consequences in 1,000 years' time. So that's a very bad idea. So putting the carbon dioxide into deep salt water filled rocks is very feasible. That's been happening in offshore of Norway since 1996, and very few people know it's happening because it works perfectly. We know how to get carbon dioxide out of the ground. We know how to put carbon dioxide into the ground, because the Americans have been doing that to get more oil out of the ground for about 40 years. So we know how to do this technically and engineering-wise. And in terms of earthquakes, then earthquakes could be a potential risk, but you can assess that geologically, because you know what the earthquake risk in regions, particular regions are, and you can also get a lot of learning out of what nature has already done, in that we know, for example, that all the oil and gas in the North Sea has stayed intact and reservoired in those oil fields for 50 or 60 or 70 million years. So if we put carbon dioxide down at those depths, earthquakes can occur and will occur, but not crack those traps, and the carbon dioxide will still stay there.
Thank you. Harriet.
Thanks so much. One of the things that we're hearing overwhelmingly from students, particularly through a What's the University For series that the chaplaincy coordinates for students and staff right across the university, is that students, particularly in the social sciences, really want the university to help them to become globally responsible citizens. So I was really interested in what you were saying about teaching, and thinking that students are wanting, whatever course they're doing, really, and we're hearing this very loud and clear, whatever course they're doing, they're wanting to be, the university to be a place that helps them to develop the character they need to be out in the world, enabling the world to become a sustainable place. Yeah. So it's an invitation to think extremely creatively about courses, programs, ways of learning, to enable students to develop in that way.
So that's, and I've perceived the same thing. That's a great affirmation, I think, of the students we've got in Edinburgh, because I also get the same type of feedback. And I think University of Edinburgh's got a good track record in being a fair trade university, trying to be a sustainable university, trying to clean up its own carbon emissions and reduce its own carbon footprint. It's achieving that much faster than comparable organisations and comparable companies and businesses, if you like. But the other thing I think we have to teach the students is that this is going to be tough, because when they go out into the real world, out there are lots of incumbent people who are 50, 60 and 70 years old who've made a lifetime's business out of behaving like this, and to ask those folks to change, or businesses to change in a different way, is going to meet with a lot of resistance, and does meet with a lot of resistance. So our students also do have to have the realization that just asking and expecting people to do the right thing just because it's the right thing isn't always going to win. You have to be smarter than that, and also realize that this is probably a long game of tens of years, not just a 5-year fix or a 10-year fix. This is going to take all of their career to move through this type of endeavor.
One last question at the back, and then...
I'm conscious that this question raises another range of ethical issues, but I wondered whether there is any research taking place within the university on whether by genetic engineering the photosynthesizing properties of plants could be isolated and enhanced and encouraged to develop in particular organisms apart from other organisms that, or other, as it were, functions that may be using up part of the plant energy and activity.
Right, okay, so I understand the question. I cannot answer about the research portfolio because I don't know. Other people may. I'll just give my answer and then other people might. But I do know that elsewhere in the world then there are breeding programs and possibly genetic programs going on to improve drought resistance in crops, etc. So we can grow biomass on larger and larger areas, and potentially that can feed into greater sustainability by producing negative carbon, etc. I thought I saw a twitch of a hand. Does somebody know anything about that? No? So I don't know. I don't know if anybody else wants to volunteer that, but no, okay. But, you know, obviously we can try and look that up if that's something you're very interested in, because it is potentially a way forward, but it is also manifestly going to meet with a lot of opposition. And I talked about the public perception and public acceptability of what, to me, is quite a simple, straightforward change of bolting an extra piece of equipment onto an existing power station. But it's very surprising how these apparently very simple changes do meet with profound opposition sometimes.
Thank you very much. I think, Mary, I think we've had to come to the end of the questions, if you don't mind. Could you pass that to Francis? Thanks. Thank you very much for all your questions.
Right, okay, pleasure.